Hi, I'm Dr. Incognito. In this video, we're going to find the local extremes for a function. So we want to find local mins and local maxes. Let's look at an example. Suppose f of x is equal to 2x cubed plus 3x squared minus 36x plus 2. If we want to find a local min or a local max, then the place we should look is at the critical numbers. So find the critical numbers. So we consider f prime of x, that's equal to 6x squared plus 6x minus 36, which exists for all x. It's a polynomial, so it exists for all x. Critical numbers come in two varieties. Either the derivative doesn't exist or the derivative is 0. So if we set this equal to 0, then we get 6 times x squared plus x minus 6 equals 0. 6 times x plus 3 times x minus 2 is equal to 0. And that tells me that either x is negative 3 or x is 2. So at these points, our curve has horizontal tangent lines. The curve y equals f of x has horizontal tangent lines, and these could be local extremes. We could have a local min or a local max at either of those points. So to figure out if we do and which type, we will consider where the function is increasing and where it is decreasing. So negative 3, 2. In a previous video on increasing and decreasing, I used this exact example and discovered that the function was increasing on the interval from negative infinity to negative 3, and then decreasing on the interval negative 3 to 2, and then increasing on the interval from 2 to infinity. We figured that out by checking to see whether f prime was positive or negative on each of these intervals. And this is what we discovered. So what's happening in x equals negative 3? The function is increasing to the left of x equals negative 3, and then decreasing to the right of x equals negative 3. And that's exactly what we expect out of a local maximum. A local maximum, you'll have a horizontal tangent line, and to the left, the curve is increasing, and then to the right, the curve is decreasing. That's exactly what we have here. At negative 3, we have the horizontal tangent line, the critical number at negative 3, and then the function is increasing, followed by decreasing. So we have a local max at x equals negative 3. And what about at x equals 2? At x equals 2, if we look at the behavior in terms of increasing and decreasing on either side of 2, we see that the curve to the left of 2 is decreasing, and the curve to the right of 2 is increasing. And that's exactly what we expect out of a local min. To the left of our critical number, the curve is decreasing, and then to the right of our critical number, the curve is increasing. So we have a local min at x equals 2. So we can find the critical numbers, negative 3 and 2, and those are our candidates for local min and local max. And then if we examine the derivative to the left and the right of the critical number to see if f is increasing or decreasing on either side, then we can make a conclusion about having a local min or a local max. And this analysis that we just did is called the first derivative test. The first derivative test for finding local mins and local maxes. So first we suppose that x0 is a critical number for f of x. So in this particular example, here's our f of x. The critical numbers were negative 3 and 2. So suppose we have a critical number, then if f prime changes sign from positive to negative at x0, which is what happened at -3. Increasing came from f prime was positive, decreasing came from f prime was negative. So there was a change in the sign of f prime at -3. F was increasing, f prime was positive. F was decreasing, f prime was negative. So at -3, there was a change from positive to negative in f prime. So if f prime changes from positive to negative at the critical number, then f has a local max at x0. That's what we saw here. And if f prime changes sign the other way, if f prime changes from negative to positive at x0, which is what we had here, f prime is negative, and then you get to 2, and then beyond 2, f prime is positive again. So if f prime changes from negative to positive, then you have the local min situation. So then f has a local min at x0. So if you want to find local extremes, one way to do it is to find the critical numbers and then look on either side of the critical number and see if there is a sign change in the derivative. If the derivative is changing from positive to negative, then you have a local max. And if the derivative is changing from negative to positive, then you have a local min. So that's one way to do it. That's the first derivative test. There is another way. So we'll look at this exact same example. We have our critical numbers, -3 and 2. Another way to find the local max is to simply take the second derivative at that point, to examine the second derivative. So what is f double prime of -3 and what is f double prime of 2? Well, we didn't calculate f double prime yet, so let's do that. Here's f prime. So f double prime is 12x plus 6. 12x plus 6. So f double prime of -3 is -30, which is negative, which means that we should interpret f as being concave down. And now we can make the following analysis. Since -3 was a critical number with a horizontal tangent line, and the function is concave down at that point, combining those two pieces of information, a horizontal tangent line and concave down, we can see that we should expect a local max at x equals -3. And in the other case, f double prime of 2, if we put 2 in for x, we get 30, positive 30. This was -30, right? -30. I missed the 0. F double prime of 2 is positive 30, which is positive. And so that means that f is concave up at x equals 2. If you combine concave up with a horizontal tangent line, the horizontal tangent line came from f prime of 2 was equal to 0. We took the derivative, set it equal to 0, x equals 2 was a solution. So f prime of 2 is equal to 0. We have a horizontal tangent line at x equals 2. And now we also know the second derivative is positive at x equals 2. So we have two facts. We have concave up and a horizontal tangent line. Those two together will give us a local min at x equals 2. So this type of analysis is the second derivative test. The second derivative test. The second derivative test says if f prime of x0 is equal to 0 and f double prime of x0 is negative, that's the first case. If f prime is 0 and f double prime is negative, then we have concave down with a horizontal tangent line, and so we get a local max. So then f has a local max at x equals x0. And on the other side of the coin, if f prime of x0 is equal to 0, and the second derivative is positive, then we have a horizontal tangent line combined with concave up, and that gives us a local minimum at x0.